Hello again, my dear students, and welcome to the third part with our sensors, or typically nano biosensors lecture. If you remember, maybe we in the first and in the second part, we have demonstrated together the idea of utilizing FETs, or organic feed effect transistor, in order to build a biosensor, and we refer to this application typically for a lactate blood sensor. And as you can see from this graph, as an output graph of this paper, you can see that this semiconductor acting as a channel connecting the source and the drain, it changes its property by the injection of different samples with different lactate concentration, leading to a decrease in the overall drain current, as you can see in this graph, by increasing the percentage of lactate in blood, the percentage of or the drain current starts to decrease. Of course, principally, this fulfills the main concept of a sensor, so that whenever we have a physical change here, it's a biomedical change in the lactate, in the form of the change in the lactate of the blood. Whenever we have this, we correspondingly have a change in an electrical parameter, which is current. However, this is in this form is not suitable to be digitally processed. I mean, usually, and based on the configuration we previously see maybe in the zero lecture and in the first lecture, in order to implement a smart sensor, you need to make some sort of an analog to digital conversion stage in order to convert your data, your sensing data, into a digital data, and then you make the necessary processing steps, and then you can use it for a transceiver to transmit it to a central node or whatever. So in order to prepare your data to be compatible for an ADC conversion, you have to convert such a change into current into a corresponding change in voltage corresponding to the expected voltage dynamic range in the ADC. For example, if your ADC is working from 0 to 15 voltage, then you are expecting to convert this variation in current into a variation in voltage in the range of 0 to 15 or whatever. So that's lead to what we can call an interfacing circuit. So the main job description of this interfacing circuit is converting the output of the sensor, which is current in this case, into a variation in a voltage that is compatible with the ADC conversion. So the question is how we can build such an interface circuit. So in order to answer this question, let me go directly to the whiteboard here, and let's start thinking together how we can build an interfacing circuit. So generally speaking, what we have is we have an organic field effect transistor, OFET. So this OFET is managed to work under a certain and a constant biasing condition. So we have a certain so let me assume that I connect the source to the ground, and then here we have some sort of biasing. Definitely the voltage applied to the gate should be greater than the threshold voltage to ensure that the OFET is turned on, is working in the active region. So that means that the voltage should be greater than the threshold voltage. And we ensure here a VDS. You can use the VDS or the drain source voltage to choose your region of operation. It can be either in the tried region or in the saturation region, whatever it is. So generally, if you remember the IV characteristic curve for a MOSFET or for a field effect transistor in general, here we have the VDS, and here we have the ID, and we have this famous curve. So by choosing the operating voltage, this voltage we call it, if you remember, VDS sat. So by choosing the voltage applied here, you can choose your region of operation either to be in the saturation region or to be in the active region. It depends. However, the key important point here, my dear students, is that during this experiment, you are going to fix the operating point of view transistor. You're operating biasing condition. I mean, the voltage applied to the gate or the voltage applied to the drain will be fixed among the experiment. The change that will occur in the current is mainly due to the change that occur in the semiconductor itself due to the interaction with lactate. That's why it will lead to a change in current or whatever. Okay. Let's go down to the proposed circuit in this direction, how we can make a interfacing circuit now. So let's see how we can make this. So this is our OFET. Then we have this bipolar junction transistor. Here we have a resistance and we have a supplying voltage of 5 volt. So this is our circuit, as you can see, and let's start demonstrating the circuit step by step. So the first important point here is that the first important point actually is this turning on, turning off node here. This is a very critical point whenever you are designing a sensor, because as you definitely know, we are considering active sensors. What I mean by active sensor is simply that these sensors are consuming some sort of power or between quotation energy. So if your sensor is turned to be a 24/7 sensor, that will count on the power consumed, or in other words, the energy, the total energy consumed by the sensor. So most likely, sensors are designed to work in a periodic manner so that sensor can detect the sensing value or the sensing parameter, which is, for example, lactate herein, in a certain duration, and then turn it off again, and so on. Herein, we can use the concept of the field effect transistors in order to apply this process simply by bumping some sort of a on-off signal, a pulse signal here to the gate of your OFET. So whenever you are applying 0 to your OFET, generally speaking, this transistor should turn off, and then your sensor is not working. Once you give it a high signal, then the transistor is turned on and it starts to sensing and so on. Basically, my dear students, it's not that on-off process, because simply, as we already studied, whenever the transistor is in off state, it still consumes some power due to the off current. I think we already highlight the parameter on off for the on-off current ratio and the subthreshold swing and all this stuff. However, we can still consider that the power consumed in the off state when the voltage applied to the threshold is 0 is still much lower than the power consumed in the on state. So this is a very basic understanding of how you can control your field effect transistor to be turned on or turned off based on your sensing needs. Now, let's assume that this OFET is turned on, and then we have this OFET structure works to measure lactate. And as we already consider that the voltage here, or the VDS here, will be kept constant during the experiment. And what will change is simply the current flowing here, which is the ID. As you can see, using a nodal analysis here, you can say that the current flowing here, which is ID, is simply a part of a total current flowing from the source to this node. So the current here, let me call it I. This I is going to be branched into some of this ID, and another will be called IP. I simply called it IP because this is the base current injected to the BGT to the right. So the first equation that can be written here is I equals ID plus IV. Now, our sensing element is reflected into ID. So whenever the lactate in the blood change, the ID, the value of the ID will change accordingly. And in a very basic electronic manner, my dear students, whenever this voltage is kept constant, which is the VDS voltage, we will kept constant this voltage because it's simply in the it is simply working in the same region. So we can assume that this I is constant. So if we assume that this I is constant and we assume a change in ID, simply a change in ID is reflected to a change in IP. So what you are going to do simply, my dear students, is whenever the ID change, IP will change accordingly. So knowing that its submission should be equal constant all the time. So that means that you have a reverse process or a reverse proportionality between the ID and IB. The higher the ID, the lower the IB, and vice versa. Now, how this affects this node? We definitely know, my dear students, that IC equal beta times IB. So when this IB change, this will reflect on a change in the collector current flowing here. So IB and IC are correlated by this beta factor, which is a constant. Let's say usually we take it for 100, if you remember, in the BGT transistors. So now this IC is going to be a reflection for ID, because simply when ID change, IB will change accordingly. When IB change, that means that this IC will change accordingly. So going to the IV characteristic curve for a BGT. The IV characteristic curve for a BGT is simply like that. So this is VCE, and this is IC. So I'm sorry, I have to make it like, okay, so very simple, very simple. When you say that the IC change, that's correspondingly mean that the VCE change. So the change of the IC and the change of VCE is correlated or is managed to this IV characteristic curve. Let's see what is our output. As you can see here, my dear students, the V output here is simply the VCE. So what you can say that, because this is a ground, so what you can say is simply that whenever the IC change, this VCE, well, it change accordingly, and then V output it change because V output is VCE. So now let me tell the story again. When this sensor is turned on, that means that this sensor is working. So we are fixing everything for the sensor except the ID or the drain current. The drain current is vying with the variation in the lactate, as we already demonstrated. So with changing the lactate concentration, the ID change. Keeping I capital constant, when ID change, IB will change in reverse. So the higher the ID, the lower the IB, or vice versa, because actually in our case, if you remember the graph, the higher the lactate concentration, the lower the ID. So when ID go down, that means that IB will go up. So when IB will go up, this means that simply IC will increase accordingly because IC equal beta IB. And when IC change, that simply that VCA will change accordingly. So you can have a voltage here corresponding to the variation in the current. And this is one of the models or one of the schematics where you can implement an current to voltage converter to be suitable to be then processed using an ADC or an analog digital converter to process or to convert these data into a digital data and so on. Definitely, my dear students, this is not the only example or this is not the only schematic that is capable to convert voltage to current, of course, sorry, current to voltage. Or in other words, this is not the only schematic that is suitable for our case. You can find hundreds, sometimes thousands of circuits or thousands of schematics that can be used as an interfacing circuit. And there is always a debate in literature. What is the best interfacing circuit for a certain sensor? Here, we have to consider a lot of parameters related to the complexity of the circuit, the reliability of the circuit, the power consumption in the on state, the power consumption in the off state, the capability to adjust the design parameter to fit a certain needs. A lot of parameters is considered in the evaluation of such interfacing circuit. So the main idea here is to get you in touch with the concept of interfacing circuit in general, how to build an interfacing circuit. However, it is impossible to limit our thinking to a certain interfacing circuit. Please feel free to suggest as much as you can interfacing circuits for any sensor and start to make a evaluation for this and a comparison between these interfacing circuits together to reach the optimum interfacing circuit for a certain sensor. That's all for the biosensing lecture. In the next lecture, we are going to still keep with biosensors, but we are going to move into another type of sensing, what we call a piezo effect sensing. In the piezo effect sensing, we have three famous piezo effect sensing. We have piezoelectric, piezoconductive, piezoconductive, piezoresistive, and piezocapacitive. We are going to go mainly toward the piezocapacitive sensors and again the interfacing circuit for the piezocapacitive sensors. See you in the next lecture, inshallah, and good luck.